All right, welcome to part 3 of our lecture video series for Monday, April 10th, where we are going to look at some applications of stoichiometry and aqueous reactions. So I've given us an example here. I've thrown a lot of information at you, so let's see if we can't kind of pull some information out and see if we can identify a starting point. So I have 35.2 milliliters of a 0.200 molar silver nitrate solution that is being mixed with 15.4 milliliters of a 1.25 molar of strontium hydroxide. I am asked two questions here. So I'm asked, is a precipitate formed? And then as a follow-up, I am asked, if so, how much is formed in grams? So to answer this first question, is a precipitate formed? This means that I need to identify our balanced equations in order to figure out if the double displacement between these two things results in any kind of formation of precipitate. So let's see if we can get our balanced equations. And in general, when you are doing aqueous reaction stoichiometry, you are going to always base your stoichiometry off the net ionic equation. So really our goal here is to identify a precipitate formed and then get our net ionic equation, because our net ionic equation in aqueous reactions, that is always going to be the recipe. Because that'll help us with this how much question. So let's start by first figuring out if a precipitate is formed at all, because if it is, then we have to do some additional stoichiometry. If it's not, then we're done, right? Because the how much would be none. So let's obtain our recipe. So let's determine precipitate formation. All right, so I need to look for what is being reacted. I have silver nitrate and strontium hydroxide. So silver nitrate solution that is reacted with strontium hydroxide solution. So if I'm going to do my double displacement and ultimately try to get my net ionic equation, I like to start by splitting up my reactants that are aqueous already into how they exist in solution, which is in their dissociated ionic form. So the nitrate polyatomic ion we have memorized is an NO3 formula with a -1 charge overall. And when silver nitrate dissociates, there's only one nitrate that is put into solution because silver and nitrate are in a 1-to-1 ratio based on the subscripts in their chemical formula. And since we have nitrate with a -1 charge, our silver has to be present with a +1 charge, but we also know based on the electron configuration, specifically the valence electron configuration of silver, that this will always form a +1 charge. It's one of our exceptions to needing that Roman numeral notation for our nomenclature of ionic compounds. All right, strontium hydroxide. I recall from memorization that the hydroxide polyatomic ion has a formula OH with an overall -1 charge. And I've put two of those into solution based on the subscript given in the formula of strontium hydroxide. And strontium is a group 2 metal, which means that when it is an ion, it has a +2 charge. And now we know that our cations are going to get new anions, meaning that the nitrate is now going to be associated with the strontium. And the hydroxide is going to be associated with the silver. So kind of down here in my scratch work, I'm going to see what happens if I were to put my ions together. And remember, you're always going to balance your charges first. So put your compounds together in the correct subscript proportion. And then we will come back through and balance the total quantity of things present after the fact. So let's see here. I've got silver and hydroxide. So silver has a +1 charge, and hydroxide has a -1 charge. So it looks like if I put these things together, silver and hydroxide, it needs to be in a 1-to-1 ratio. So I will make AgOH. I don't know what its phase is yet because I have not figured out, according to my solubility rules, if this thing is soluble. And now let's look at our strontium and nitrate. So strontium has a +2 charge and nitrate has a -1 charge, meaning we need 2 nitrates in order for this to come together with strontium to form a charge-neutral compound. So the ratio is 1-to-2, cation to anion. So if I were to write this formula, this would be SrNO3, 2. And again, don't know about its solubility. So let's find our solubility rules. Where are those bad boys? Got so many tables in here. Nope, that's the activity series. Nope, those are heats of formation. Nope. Ah, here we go. All right. So it looks like I have a hydroxide rule, which says all hydroxides are insoluble unless they have sodium, potassium, barium, calcium. Strontium hydroxide is soluble. And then we've got our nitrate rule, which says that all nitrates are soluble. So we've got the fact that nitrates are soluble and hydroxides are insoluble unless we've got some of our kind of group 2 metals with them. Meaning that my strontium nitrate product, this is going to be aqueous. And my silver hydroxide is going to be forming an insoluble solid precipitate. So PPT or solid. All right. In order to get our net ionic equation, which is our recipe, we're going to have to get our complete ionic equation. So first and foremost, yes, a precipitate is formed, silver hydroxide. And let's first balance our overall molecular equation so we can then get our complete ionic equation. So looking at this, I've got, let's see here. One silver, one nitrate, 2 nitrates. That's not good. I need to double my nitrates. In doing so, I'm doubling my silver. And when I double my silver, Then I am also doubling my hydroxide, which is great because I had two hydroxides here, meaning that everything that I did in my scratch work, all of these quantities need to be doubled. For our silver and nitrate, and also for our product. All right, let's write out our complete ionic equation. So this is going to be 2 silver ions coming together in solution with 2 nitrate ions, with 1 strontium cation and 2 hydroxide anions to form 2 silver hydroxide solids. I do not dissociate this in my complete ionic equation because it is insoluble, so it does not dissociate at all. And then strontium and nitrate. And then, of course, the goal from this was to try to get my recipe, which is my net ionic equation. So my net ionic equation is going to cancel out any spectators. So spectator ions are ions that did not directly participate in the chemical change. They are ions that appear both the same on the reactant side of the arrow as they do on the product side. So I've got 2 nitrate ions to start and 2 nitrate ions at the end, meaning those ions were just hanging out in solution. They did not do anything chemically. And then I also seem to have my strontium cation as a spectator. It was just in solution before and it was in solution after, meaning that my net ionic equation is going to be 2 silver ions coming together with 2 hydroxide ions to form 2 silver hydroxide products. And I cannot reduce this 2, 2, 2, because it all looks like 1 to 1 to us, ratio, because that would mess with our overall balancing that came from our molecular reaction. So I've got everything in a net 1 to 1 ratio, but written as 2 to 2. Okay, so yes, we have formed a precipitate and we've obtained our recipe. So in the next part of this question, we are asked, if so, how much is formed in grams? So we need to figure out how much of this is made in grams. And in order to do that, we need to do a limiting reactant analysis. Because remember, we didn't just mix together exactly 2 moles of silver and 2 moles of hydroxide. That's just the ratio that this reaction needs in order for the reaction to proceed. We have information about what we actually mixed together. We know our pantry because our pantry was given to us in the form of lab quantities. We have volumes and concentrations of each of our reactants. So we need to figure out if those moles of reactants, when completely consumed, form some amount of product, and then do a comparison because we know that whichever reactant forms the least amount of product is the limiting reactant. So I'm going to break this video up into 2. We'll continue this example in the next part.